Grigory Solomadin from University of Science. About which evaluate homology of moment and complex quotients and spectrology.
Thank you. Before starting, I'd like to thank Professor Masuda for inviting me to this conference, and Kuroki-san for inviting me to Japan. Well, yeah, so this talk is about moment angle complexes and their quotients with respect to natural actions of tori and well, other groups. This is a important object of toric topology, and there are many approaches to study the homotopy types and cohomology of these spaces, orbit spaces, including spectral sequences, for instance, SER spectral sequences, which we have already seen last 2 days, and Eilenberg-Moore spectral sequence. Right. So in this talk, another, different spectral sequences will be introduced, and the relation with very well-known ones will be explained. So a brief motivation for the talk. So we consider the group action on the moment angle complex of any closed subgroup in the natural acting torus on the moment angle complex, or MAC for short. I will use this shorthand for moment angle complex and what follows. And the orbit space has a residual action of the quotient torus. So if we quotient by the global stabilizer, we have still an action on the orbit space by the residual group. Well, and we can ask what are the cohomology groups or rings and equivalent cohomology rings of such orbit spaces, and for instance ask for what is a torsion in the groups or Betti numbers, and we will cover these problems or topics using spectral sequences. So the plan of the talk is to focus on some known results on the cohomology groups of quotients, then to discuss homotopy decomposition for such spaces and their Borel spaces. After that, we introduce the Busfield-Kahn spectral sequence originating from the homotopy decomposition, and prove its collapse, a collapse type result for such a spectral sequence for every toric diagram, which is quite nice class of diagrams, including those appearing in the decomposition. And finally, we will discuss how to treat the second page of the spectral sequence, because it collapses at page 2, and in order to compute the cohomology of the target, we need a good approach to the page 2 of this spectral sequence, and we will use Schiff cohomology to describe it. So let me fix the notation. Well, this is kind of standard topic for toric topology. So we have a pair of topological spaces. A is closed in X, and the I product of such a pair is introduced by the following formula. So it is a subspace of the Cartesian product of X and times with itself, and we take X at the index I if I belongs to I large, and we take smaller set otherwise. And these I products are embedded into each other if the simplices, the indexes of these products are embedded into each other, and so these spaces form a diagram that is a functor or a small category cat K. And small category, this category is just a category of simplices in the simplicial complex K on the vertices. This is a vertex set of the simplicial complex, together with an empty set, the initial object of the category cat K, and we have arrows, the inclusions of these simplices. So it is a very simple category, quite simple category, and we consider diagrams over this category. For instance, the diagram of I products. And the definition, which was first given by Gustav Panov of moment angle complexes, is as follows. It is a well, also known as polyhedral product, the union of the I products in the polydisk. And here we incorporate two cases, complex case and real case, depending on the value of d. So complex case corresponds to d equal to 2, and real case corresponds to d equal to 1. And well, we will use the Davis-Januszkiewicz notation for the real or complex torus. So complex torus will be a compact torus in this talk, and the real torus will be just a group of two elements, having group of two elements, and we consider also coefficients R or C. Well, so this space, the union of these I products, the polyhedral product or moment angle complex, has a natural group action. So to introduce it, we consider the standard action of the torus on the disk given by rotation in a real or complex line. And this action preserves the boundary of the disk, and by taking products, it induces the action of the n-dimensional torus on the polydisk. The I products are invariant with respect to this action, so we have action by restriction from the polydisk to this invariant subset. So we obtain the action of the torus on the moment angle complex. And one can choose any closed subgroup in the torus. In other words, it is a Z2 linear vector subspace, a discrete subgroup of the real torus, and a quasi-torus that is a product of discrete abelian, finite abelian group with the compact torus, and consider the orbit space. So the orbit space will be called a quotient for the moment angle complex, and it has the natural residual action of the quotient torus. We will denote this quotient by LD. So what are examples of such well-known spaces appearing by applying this construction? These are moment angle complexes themselves, the real and complex one. Partial quotients, so-called partial quotients corresponding to freely acting subgroups HD on the moment angle complex. If we consider a more general class of almost free action, that is, the isotropy groups are all finite, then it is another interesting class. For instance, those will be toric manifolds and orbifolds, and small covers, depending on complex or real case, respectively, where we choose H to be a condimension N subgroup in the torus, and K to be the dual to the boundary of a simple polytope in Rn. And another extreme case would be the contractible space, the realization of the cone over a simplicial complex corresponding to the largest subgroup in the torus. So yeah, what are the known results about cohomology of such spaces? So, we will mention several results. The first one goes back to Hoster, who studied algebraic problems, Tor algebras of Steinweiser, I think. But his results apply well for the cohomology of the moment angle complex. So this is known as Hoster formula, and it describes the cohomology of the moment angle complex in terms of the restrictions of the simplicial complex to the vertex subsets. So Kg is the induced simplicial complex on the vertex J, and we have cohomology of such simplicial complexes on the right-hand side. Yeah. So Voskakov, Bushtaber, and Panov, in a series of papers, upgraded this formula to an isomorphism of rings, and they described cup product, in other words. Biffed, De Concini, and Procesi computed the equivalent cohomology ring for any partial quotient. The answer is given by the standardized ring, which is a quotient of degree 2 generated polynomial ring by the ideal square-free monomials corresponding to all non-faces of simplicial complex. And Danilov and a couple of years later, Yurkevich described the cohomology of projective non-singular torque varieties and manifolds in terms of the quotient of this standardized ring by a linear system of ideal generated by a linear system of parameters. And well, there is a similar result about cohomology of quasi-toric manifolds. And Bushtaber and Panov, starting from 98, this gave the proofs of the result about cohomology of partial quotients in terms of the Tor algebra of the standardized ring with various model structures, but their proof was their line of argument was incomplete. So they used Ellenberg-MacLean spectral sequence. I think I made a mistake saying Ellenberg-Moore. I meant Ellenberg-MacLean, of course. Spectral sequence, and this was fixed by a very recent paper of Matthias Franz, who completed the argument and, in fact, introduced the another product on the Tor module, which differs from the natural product on the Tor algebra. If 2 is not invertible in the coefficient ring. If 2 is invertible, then the twisted product coincides with the usual product on the Tor algebra. But if it's not invertible, then it is a different product structure on the left-hand side. So this is quite a lot of results. Let me continue so we can consider different cases of different families of such orbit spaces and try to compute the respective cohomology rings. For instance, if we fix a coloring of vertices, so lambda is just a k color. Yes. So we color the vertices of the simplicial complex by k colors by the map lambda. And if we consider the diagonal tori in the two-dimensional torus as the i's factor times j's factor in the large n-dimensional torus, I consider here a complex case, of course, then we can form the following subgroup. This subgroup consists, is spanned by such diagonal small tori corresponding to the same pairs of vertices colored by the same color. And the result of Yu Li, quite recent results, describes the cohomology of such quotient of the moment angle complex in terms of cohomology of restrictions to a bit different set of indices. So now J runs over the set of colors, not over the set of vertices. So this can be regarded as a Hochster type formula because in the case when we take the trivial, the different coloring, we color each vertex by this distinct color, it coincides with the Hochster formula. And the quotient is not necessarily free.
Yeah. So here coloring is any coloring, any map, or some proper coloring.
What do you mean by proper?
Yeah, I mean that vertices are connected, then they should be assigned different colors or
No.
any color.
Any. I think any. So another result is given by choosing K to be a very symmetric simplicial complex, the simplicial complex of faces in the m-1 dimensional simplex, and the faces have dimensions not exceeding K. So this is can be seen as uniform matroid, for instance. But it is just a very symmetric simplicial complex. The first thing to mention is the result of Grigory and Terrio, who described the homotopy type of the moment angle complex as a wedge of spheres of the following dimensions. So the cohomology can be obtained by using Hochster formula, but they obtained a stronger result by describing the homotopy type. So now we choose H, the subgroup in the m-dimensional torus, to be the diagonal circle subgroup. So it is given by exponents whose e to the power of 2p I t in all the coordinates of the compact torus. So this is a large diagonal, the circle, and we can consider the quotient to be partial quotient if k is takes those values. And Xinfu quite recently once again obtained the homotopy type of such space. So in the right hand side we can see a wedge of the complex projective space of complex dimension k+1, and together with the wedge of spheres. So this space can be further decomposed by using the previous result, and we can of course decompose the joints of sphere and wedge of sphere and sphere and the torus by the usual formula for the suspension of the product. So yes, this is a nice result. So in what follows, we will be using stabilizers. So let me explain what are stabilizers of the actions on the moment complex and its orbit space. So we introduce the following constructible subset in the moment angle complex. It is given by the points whose zero coordinate, whose coordinates are zero exactly when the respective index belongs to I. I is some fixed element of the simplicial complex. So this is some constructible subset obtained by a combination of taking complements and intersections and unions. So the moment angle complex is a disjoint union of such spaces and the orbits, and since these subspaces are invariant with respect to the torus GDM action, we have the decomposition of the orbit space into the respective orbit spaces of zeta i's invariant subspaces. So stabilizer is just a subgroup leaving of elements leaving the point x invariant, and we can describe the stabilizer of the HD action on the moment angle complex as follows. So x for x running over this subset zeta I, the stabilizers are the same, and that is why we introduced such subspaces, constructible subsets in the moment angle complex, and the stabilizer of the residual action on the orbit space with respect to the action of HD is described as the quotient of the coordinate torus. This is just the product of coordinate rank 1 subgroups by indices from I large and well, trivial subgroups in the remaining coordinates, and we take its quotient by the intersection of the group HD in the m-dimensional torus with the coordinate subgroup. And in particular, all the stabilizers of this residual action are connected. So if we look at I powers and their orbit spaces, we can see that stabilizers and consequently orbits are in general different. If we fix I and vary at a point, then stabilizers can be different in general. So this is a brief remark. So we can arrange these stabilizers and well related groups in the following commutative diagram. This is just an auxiliary well, easy lemon. And here we have two indices, I and J. These are embedded simplices into each other from the simplicial complex K. So we allow one of them to be empty. That's why we consider cat K, not K. And yeah, we have monomorphism on the left-hand side, vertical arrow, and we have projection, the obvious projection on the right-hand side, because the denominators, this group embeds to this group, and we have identity map, vertical map here. And well, the horizontal arrows are also not difficult to describe. So I made it. So we can use this commutative diagram to define Ketke diagrams. And these diagrams will have as objects abelian groups. In the real case, real tori, and in the complex case, connected abelian groups, so compact tori. And all arrows in these diagrams will be group morphisms. So the objects of, well, the object of the diagram SD is given corresponding to simplex I, element of a small category is this group, and the object of QD corresponding to the simplex I is the following quotient group, and the arrow from corresponding to inclusion of simplices from I to J is given precisely by this arrow for SD and such arrow for QD. So we now have two new diagrams, SD and QD, and we will call them the stabilizer diagram and the quotient diagram. Why? Well, because we have seen that this group is a stabilizer of the residual action. So we can call it the stabilizer, and we call the corresponding diagram the stabilizer diagram. And we have these quotient groups. We will call the diagram Q the quotient diagram. I will explain in a moment why. So what are these diagrams? What do they describe? We can take colimits of such diagrams. So basically, if we fix any closed freely acting subgroup H in the m-dimensional torus, and the action is on the moment angle complex, so by taking the colimit of S in a complex case, so 2 denotes the complex case here, we obtain a union of coordinate subgroups in the torus, m-dimensional torus, and this is what was called a toric configuration by Yuzvinsky in his work, Sergei Yuzvinsky. And if we compose this diagram with a classifying functor, or assigning, for instance, to S1 CP infinity, and which respects the products, Cartesian products, and homomorphisms of groups, we obtain the usual construction called Davis-Januszkiewicz construction. It is a subspace of CP infinity to the power of n. So these are quite well-known spaces, and their cohomology rings are exterior and symmetric Stanley-Rice rings. So exterior means that we take a similar formula, but we define the degrees of the generators to be 1, and well, this already appeared. So we have the description of the cohomology of Davis-Januszkiewicz space in terms of the Stanley-Reisner ring. So these are good diagrams because they give well, good spaces when we apply coordinates and classifying function. So let me mention one more result about cohomology of a certain family of quotients. It will correspond to the boundary of M gone with M vertices. So one can compute as an exercise the beta numbers of the moment angle complex by using Hoster formula, for instance. And now we choose H to be a subtorus acting freely on ZDK. So the orbit space is a partial quotient, and we require a certain condition to be satisfied, namely the dependence condition. So the stabilizers of corresponding to the maximal simplices of K, well, these are just the following rank 2 subtori, and we require that the stabilizers corresponding to the neighboring two maximal simplices, that is for any two vertices connected by an edge. These subgroups are spanning a rank 2 subgroup in the residual force. So I think rank 3. So there is a type rank 3. So in a sense, this is a condition similar to the GKM condition when we have for two edges of the M-gon connected by another edge, we have the condition that all these three edges span a two-dimensional vector space. So this is why it is called a dependence condition. So this was introduced by Liu and Zhang in the paper of last year, and they computed the cohomology groups of such partial quotients corresponding to M-gons. So they show that the cohomology are torsion-free and compute the beta numbers. So we see a general pattern that if the cohomology of the moment angle complex is torsion-free, then any partial quotient that we have seen has also no torsion in its cohomology. And I will present it later a result, a related result. So now let's discuss homotopy decomposition for any quotient of moment angle complex in this Borel space. So I need additional toolkit in order to formulate results. So the first one is a model structure and a category. A model structure is, informally speaking, a collection of morphisms of three types: weak equivalences, fibrations, and cofibrations satisfying certain axioms. I'm not going to give them right now, but what this model structure on a category allows, it allows to do a homotopy theory in various categories. For instance, in a category of topological spaces, we take this three families of morphisms to be weak equivalences in the usual sense, fibrations and maps having left lifting property with respect to any acyclic fibration, that is Ser fibration, which is a weak equivalence. And equivalently, the last family of morphisms, continuous maps in the category of topological spaces can be described as retracts of relative CW complexes consisting of such maps, continuous maps. We then equip the category of diagrams over a small category cat K with values in topological spaces. So these are objects of such category are well, diagrams whose objects are topological spaces and arrows are continuous maps. We can equip such a category with a model structure in order to perform homotopy, well, homotopy computations in this category of diagrams. This is called a ready model structure, where there are different structures, but we consider this particular structure. It consists of three, once again, families of morphisms. These are object-wise weak equivalences of diagrams. So a morphism of diagrams is just a collection of arrows between all the objects of diagram corresponding to the same objects, which are commuting with all the arrows in the diagram. So we say that here we take here morphisms of diagrams consisting of weak equivalences of topological spaces on each level, on the level of each object. Then the fibrations will be object-wise self-fibrations, so maps consisting of object-wisely self-fibrations, and finally there will be more difficult to describe, more tricky family consisting of maps such that for any I, so I is a simplex of K or an empty set, for any I, the following map is a cofibration, and here LIE is called a latching object. It's the colimit of objects corresponding to all simplices, proper simplices in the simplex I. So you can consider this as a colimit of the diagram or the boundary of the full simplex on I vertices. So this has to be a cofibration, and this will be cofibrations in this category. Okay, so now we can define homotopy colimit of the diagram D to be the left-derived functor to the colimit functor of D. And you can, well, more explicit way to define this is to make a cofibrant replacement of D. This is a thickening of the diagram, and then you apply to this thickening the colimit functor and obtain the homotopy colimit. And there is a Busfeld-Kampf formula, which is some co-equalizer of certain diagram of two arrows. So the thickening of the diagram D will correspond to this additional factor. This is the nerve of the undercategory corresponding to of all simplices, well, of all arrows starting from the simplex I. And we need to reverse reverse arrows in such category, then apply the nerve. So this thing is contractible, so because it has the least, the category has the initial object, so this can be regarded as a thickening of the diagram. And then we apply colimit and obtain the homotopy colimit. All right, and another tool that we need is called simplicial sets and objects. So to describe what is a simplicial set, we introduce the category of non-empty finite linearly ordered sets as objects and order preserving maps between them. And there are in particular the following arrows in this category called face map and degeneration map. And the face map is given by omitting the case element in the ordered set n on n elements from 0 to n. I mean n plus 1. Yeah. and the degeneration map will drop, well, will repeat the case element in this ordered set. So we allow repetitions. All right. And what is a simplicial object in a category C or a cosimplicial object? It is a functor from this category delta with reversed arrows from delta up to C. And this is called a simplicial object. And if we take just functor from delta without reversing the arrows, it will be called a cosimplicial object in the category C. Equivalently, to describe a simplicial or cosimplicial object, one can give the collection of all simplices, so just objects in the category C, and degeneracy and phase maps satisfying the simplicial identities, which are satisfied in the category D. So there are 5 kinds of identities involving these morphisms. I will not write them down because it's quite lengthy, but it's quite standard material about simplicial sets. So yes, a simplicial set in the category is just a bunch of objects set and generating maps between them, satisfying certain identities, simplicial identities. And then we can start from a diagram and produce a simplicial object in the category of its values by the following formula. So the set of the collection of simplices of this simplicial object will be given by the coproduct of objects of the diagram D, and there are quite obvious phase and degeneration maps given by dropping out the respective element and repeating the respective element in the chain. So the coproduct is with respect to all chains in the indexing category of K. So we consider cat K diagrams. So this will be just a chain of simplices embedded into each other. And in the case when we drop out the last object, we need to apply here the composition with the arrow of the diagram, and similar argument is needed to define the degeneracy arrow in the extreme case. And cosimplicial replacement for a diagram is defined similarly, but we need to consider a diagram as a covariant. We need to consider D as a contravariant functor and use coproducts instead of products, and also take not DIN but DI0 terminal object. So yeah, this is a way to produce a simplicial or cosimplicial object from a diagram. And one more thing which is very important and related to simplicial sets is a geometric realization of simplicial topological objects, or simplicial topological spaces. These are simplicial objects in the category of topological spaces. So we can just take all the simplices in the simplicial set and glue them along the phase and degeneracy maps. And a formal way to say this is to consider the coequalizer of the following diagram. And here two arrows are defined using this arrow in the additional category, indexing category, by pre and post composing with this with the factors of this product. So there are 2 arrows, and we take a coequalizer in order to obtain a topological space for any simplicial topological space. This is called a geometric realization. And why we need it? Because the homotopic limit of a diagram in topological spaces can be obtained, well, almost by definition, as a geometric realization of the simplicial replacement of these. So we start from a diagram, topological spaces, we replace it, we obtain a simplicial object, in simplicial topological space, then we apply geometric realization. This would be homotopy equivalent to the homotopy limit of D. So this is how these two theories meet each other. And the formation of homotopic limits is natural with respect to morphisms of diagram. And we need also one more definition. A Ketke diagram is called cofibrant, Ketke diagram D, if the following condition holds. So we form the colimit over the boundary of each simplex, and the natural mass from the colimit to the object of the diagram corresponding to the whole simplex must be a cofibration. Such diagrams are called cofibrant. And yes, these are cofibrant objects in model category, but we will not need. So what are main tools? So we look at these two, two theories as a toolkit. So we need some useful tools related to homotopic limits. And the first tool is called the projection lemma. It says that if D is cofibrant, then a homotopic limit up to a homotopy can be computed as the colimit of the diagram D. And the second important statement is called homotopy lemma. It says that if a morphism of diagrams consists of homotopy equivalence, weak equivalences, then the induced map of the homotopic limits is a weak equivalence. Or if we, for instance, consider diagrams of CW complexes, for particularly nice diagrams, we can replace weak equivalences to homotopy equivalences. And for instance, the diagrams, the stabilizer and composition with the classifying factor diagram are cofibrant in this sense, because you can check this by hand. These arrows are just embeddings of closed subgroups into a larger subgroup, or embeddings of closed union of closed subsets into CP infinity to the power of n. So the first theorem of our joint project with Van Limonchenko is the following. Homotopy equivalence, we describe the orbit space of the HD action at the homotopic limit of a certain diagram. This is precisely the quotient diagram we've seen before. And this homotopy equivalence is equivalent with respect to the action of the residual torus. So there is a natural way to define the action of the residual torus on the right hand side, and this homotopy equivalence is equivalent with respect to the left and right side actions. And this result was known in various particular cases. So excuse me, how much time do I have when do I have to start? 50 minutes. Okay, I have to increase speed. So yes, this is a useful result. Let me explain why. I will skip the proof. So what is a Borel construction? We have diagonal action for any G space X diagonal action on the product of the universal bundle and X, and the orbit space is called the Borel construction, and the cohomology is called the equivalent cohomology of X with respect to G, and we can describe the Borel construction as a colimit of the composition of classifying factor with the stabilizer diagram. And for instance, for any partial quotient, we obtain here the Stanley-Reisner ring, well, taking the respective coefficients. So there is a way to define Ellenberg-Moore spectral sequence and describe it explicitly for general quotients, not only freely, for orbit space, for not only freely acting subgroups, and it looks like this, and corresponds to the self-operation. So F is a homotopy fiber of the, and this is the total space is a Borel construction, and the base is a classifying space of the residual action. And we can describe the homotopy fiber as a orbit space. Let me skip the result. So it was known for the case of partial quotients that this spectral sequence computing the cohomology of the partial quotient collapses at page 2. It was proved in a series of papers eventually, but the abutment of this spectral sequence is non-trivial, and we can see this on the level of RP3. So we take K to be 2 disjoint points and H to be element 2 subgroup in the large diagonal circle, and we can see that the generator of H1 sits here, but its square is non-trivial. However, in the spectral sequence, its square is trivial. So this is like a no-go result to use the collapse result of EMSS in order to describe cup product in the cohomology of partial quotients. So yeah, so I'm a bit slow. So let me just explain the idea. We associate, so there is a way to associate to any homotopic limit of a diagram of topological spaces spectral sequence in natural way. So it is firstly defined for any simplicial topological space as the Serre spectral sequence corresponding to the filtration by simplicial degree, and for any diagram we just take the simplicial replacement and apply this definition in order to obtain this spectral sequence. So this spectral sequence computes eventually the cohomology of the homotopic limit, and it is precisely what we need, but we need a collapse result, and we could prove this result, the collapse result, for a wide class of diagrams, namely toric diagrams. I recall these have in complex case, for instance, as objects compact tori, and the arrows in a toric diagram are always homomorphisms of tori. So we could prove the collapse result in such a wide class of diagrams. And also for compositions of such diagrams with classifying functors, we also could prove the collapse result. And yes, it's kind of long, and we use formality for diagrams. This is a notion which was introduced by these 3 authors who try to compute cohomology of a space of long nodes. So it's a totally different subject, but we could apply their toolkit for our situation, and we use the bar construction in order to construct a zigzag of quasi-isomorphisms. Let me skip this because I'm kind of running out of time. So yeah, so I need to skip the slides. So eventually we could prove the following technical results. That there is a chain of quasi-isomorphisms between the cohomology of the torus and its DGA of normalized cochains, and this zigzag of quasi-isomorphisms is natural with respect to any homomorphism of tori. So there are vertical arrows. You can see there are vertical arrows. So this zigzag of quasi-isomorphisms is natural. That is why we have a zigzag quasi-isomorphisms for a diagram. And this is the main statement that we need in order to prove collapse result, to prove that the diagram is formal. So there is a chain of quasi-isomorphisms between the diagram and its DGA of simplicial normalized chains. But let me say that this notion of formality is not preserved under colimits. For instance, we know by the result of Denham and Suciu that there are lots of moment angle complexes that are not formal. So this notion of formality for diagrams coincides with the usual notion of formality for the trivial diagram, indexing diagram, when we have one object and one arrow. But the point here is that the formality for diagrams is strictly, the usual formality is strictly stronger than the formality for diagrams. And yes, we could get a grip on cohomology of moment angle complexes by using this collapse result. So we need an additional toolkit of sheaves over offsets and their cohomology. So a cosheaf is basically a functor from a small category with reversed arrows to a category of abelian groups, or finitely generated abelian groups, I mean. And we can additionally form another simplicial complex of the non-degenerate simplices in the north of the category cat K. So this is can be described as the collection of chains of embedded simplices in the simplicial complex K, but we also allow empty set. That is why there is not K but cat K, and topologically it's nothing but the cone over the barycentric subdivision of K. So we consider this simplicial complex, and for any cosheaf or cat K that is a contravariant functor from cat K to abelian groups, we can define the refinement of the sheaf by following Matthew Carey and Anton Eisenberg works and many others. This is a quite usual notion of refinement. So by a cosheaf on cat K, we can assign a cosheaf on the refinement with simplicial complex. And finally, we can define the cohomology of the sheaf on the simplicial complex M cat K as the cohomology of the complex generated by products of chains with the respective arrows of the groups from the cosheaf, and with a differential given by this kind of usual formula. So in the last command, when we add a simplex to the last element of the chain, we need to use the arrows in our cosheaf. We define cohomology of a sheaf, or refinement of the cosheaf. So given diagram D, we can describe the page 2 using cohomology of sheaves as follows. Basically, the PQ's group of the page 2 of the Busfield-Kahn spectral sequence is nothing other than cohomology of the cosheaf, the sheaf, the refinement of the cosheaf, which was defined on the previous slide. And here we take the refinement of the cosheaf of cohomology. This is just the functor obtained by composing D with the cohomology of topological space. This is a diagram in abelian groups as well as in abelian groups. So yes, and if we look at the collapse result once again, then we see that the singular and equivalent cohomology of the orbit spaces of moment angle complexes are direct sums of cohomology of certain sheaves. And if we consider the real case, then the situation simplifies drastically, because then the spectral sequence will be concentrated on page 2 in the one row, namely the 0 row, because the objects of the diagram are discrete spaces, so their cohomology is just concentrated in degree 0. So it is not very interesting to consider, but we can, for instance, with zeta2 coefficients, obtain the cohomology of quotients of real moment angle complexes, partial quotients, I mean, with zeta2 coefficients here as a Tor algebra. And we can relate this, well, new and strange spectral sequence with well-known Ellenberg, MacLean, Ellenberg-MacLean spectral sequence by an additional algebraic spectral sequence. We call it a comparison. Well, I call it the comparison spectral sequence. So in a sense, and informally speaking, it starts from the page 2 of the Busfeld-Kahn spectral sequence, and it converges, sorry, not the other way around, starts from the page 2 of the Ellenberg, MacLean, Ellenberg, sorry, and Moore, right? Spectral sequence and converges to the page 2 of the Busfeld-Kahn spectral sequence. But notice the additional grading in this spectral sequence by variable t. So in a sense, it measures commutativity of Tor and limit functor because of this computation. So we have composition other way around, and it is computed as on the right hand side. So these limits are derived functors of the limit functor, and they can be also described as the cohomology of a sheaf. So cohomology of a sheaf on ncat k. It can be replaced by isomorphism with a cohomology of a sheaf. So in the example of the trivial quotient, the moment angle complex, we obtain isomorphism between the components of the Tor algebra with the components of the Busfeld-Kahn page 2 elements, groups from the page 2 of Busfeld-Kahn spectral sequence, and everything agrees in this case, because we know that cohomology of the moment angle complex is described by Ellenberg, AMSS, and BKSS. These are this. So let me skip the construction of the spectral comparison spectral sequence. I need additional notion of recurrent formality. So sorry, how much do I have? Oh, so I ran out of time, right? No? Oh, okay. So 2 minutes. Okay. So there is a notion of recurrent cohomological formality over zeta. This is a notion defined for any t space X, and it basically is the condition that the Serre spectral sequence of the Borel construction collapses at page 2. Well, there are equivalent formulations. For instance, fiber inclusion induces the epimorphism, and in terms of the Tor groups, yeah. So what I wanted to say that for a class of equivalently formal partial quotients, we can use these collapsed results and the description of the second page to obtain some nice formula for the Busfeld-Kahn elements, the groups from the page 2 of BKSS. And this can be understood as a refinement of EMSS collapse for such kind of quotients. And Danilov in 1978, obtained a similar result, vanishing except diagonal, for toric projective non-singular varieties using Hodge structures. So this can be considered as a generalization of his results because toric non-singular projective varieties are partial quotients and they are equivalently formal. Yeah, and one more thing to say that we can compute the beta numbers of such spaces by the following nice formula just by summing up the Euler characteristics of the sheaf cohomology, and I think this is a new result. And this formula agrees with the case of projective, well, quasi-toric manifolds and toric varieties, projective toric non-singular varieties, because in this case, the right hand side can be checked that it coincides with the H numbers of the corresponding polytope. So this is some generalization of the description of beta numbers for quasi-toric manifolds for equivalently formal partial quotients. So yes, so there are something more, but I'd like to stop. I'd like to stop here. Yeah, because I ran out of time. Sorry, I'm sorry. So yeah, this is our paper with Ivan. It is published, and it is expected that the other results will appear in my preprint this year. So thank you for your attention.
Please tell me about the example of the equivalently formal partial quotient, which are not torus manifolds.
This is a good question. I'm not sure I can give such an example right now, but it would be interesting to describe such spaces. So these are spaces having vanishing odd cohomology, and there is equivalent formality. So in a sense, you can use freeness of the HPT module to describe these beta numbers, but we had announced we have such an answer. I showed this again. So this is kind of nice formula for this family of spaces, but it would be interesting to find something more. But I think if a family has toric varieties and quasi-toric manifolds, it must be interesting. Yeah.
Now we consider the algebra structure of by using both field components.
I'm not sure, because you need to choose a model model category.
So
Maybe there.
it is important to consider the algebra structure of the square things because
Maybe there are results. I'm not sure. Voivodsky, but I'm not sure. This is a good question to generalize for algebraic category. Okay.
Okay, so the first day is over. So tomorrow we start from the 10 o'clock. So please join tomorrow.
it's very enough.